Okay, so we are going to look at how we can approximate this differential equation numerically and solve it. So we're going to look at some general principles. The method that we're going to look at is called the finite difference principle, or the finite difference method. And this relies on approximating the derivatives. In this case, there's just a second derivative as a difference rather than a continuous limit type of thing. And so we're going to go through this. We're going to look at the equation minus u double prime is equal to f. F is given. And we want it to be on the interval 0 to 1. Now, this is a second order differential equation. And if you think about your differential equations class, if you looked at an initial value problem, you needed to know the differential equation, and then you needed to know u of 0 and u prime of 0 to be able to get a solution. This is something similar. It's called a boundary value problem. There's actually a lot of differences between initial value problems and boundary value problems. But what we're going to do is we're going to specify the values of u at the endpoint here. And we're saying that u of 0 is equal to 0 and u of 1 is equal to 0. These boundary conditions are called Dirichlet boundary conditions. There's other boundary conditions when we specify the values of the derivatives. Like we might want to specify that u prime of 0 is 0 and u prime of 1 is equal to 0. Those are called Neumann boundary conditions, and then there are mixtures of those that have various names. Robin or one is one in name, but sometimes they're just called mixed boundary conditions. But this is the problem that we are going to work on discretizing and solving numerically. Okay, so this is going to be kind of our prototype, and then we're going to see how we can modify this to look at a more general type of differential equation in one dimension, and then we're going to look at how we can do this in 2 dimensions as well. Okay, so I made the video that you are watching right now, and I realized that I'm using Taylor's theorem a lot throughout the video, but I have not explained yet in this class what Taylor's theorem is. Now, if you've had Calc 2, you've seen Taylor's theorem, and hopefully you've seen Taylor's theorem after that as well. But I know maybe some of you, it's been a while since you've seen Taylor's theorem, and maybe in your calculus class you didn't really even understand what was going on with Taylor's theorem. So I just want to remind you of what Taylor's theorem is. So let me just begin with the fact that if we have some function, I'm going to use u of x as the function instead of f of x because that's the letter that we're using in this class. If u of x is equal to a power series like this, the sum k equals 0 to infinity of ak ck x minus a to the power of k. Okay, if u of x is equal to a power series like this, then Taylor's formula says that ck is equal to the kth derivative of u evaluated at a divided by k factorial. Okay, now that is a huge assumption. If u is equal to that, then these are the formulas for ck. Now, a function that satisfies this is called an analytic function. Most of the functions that you know from calculus and stuff like that are analytic functions, and there's a good reason for that. But a lot of functions are not analytic functions, and so this isn't true. And we really want something like this to be true. So what Taylor's theorem says is the following. So Taylor's theorem says the following. It says that u of x is going to be equal to the sum k equals 0 to n of the kth derivative of u evaluated at a divided by k factorial times x minus a to the power of k. So this is, I'm going to write something over here. This is not correct yet. Okay, this is just the first n terms of a Taylor series, and then it's going to be plus the n plus 1th derivative of u evaluated at some number c divided by k factorial times x minus a, this is n plus 1 factorial times x minus a to the power of n plus 1. So in the case that n is equal to 0, this is just the mean value theorem. So the Taylor's theorem is a generalization of the mean value theorem. And here, what is C? We don't know anything about it, really, by just this formula. Here is between x minus a, between a and x. It's some number between a and x. Okay, so we are going to apply this in a way that looks a little bit different from this. Let's see the best way that we can sort of think about what this is going to be. Instead of using x as the variable here, I'm going to call it y. So this will be y here, and this will be y here. Okay, and how we want to apply this is we're going to say that a is going to be equal to x, and y is going to be equal to x plus h. So how is this going to work? U of x plus h, okay, y is equal to x plus h. This is one way to derive this formula, not the only way. Okay, so u of x plus h then is going to be the sum k equals 0 to n. Okay, we're going to look at the kth derivative of u evaluated at a, but we're just calling a x right now, divided by k factorial. Now notice what's going to happen here. Y is x plus h. X plus h minus a, that's x plus h minus x. So this is going to be h. So we're going to have times h to the power of k. And then over here, we're going to have times the n plus 1th derivative of c divided by n plus 1 factorial. And again, here, we're going to have h. Sorry, that should be a plus. H to the power of n plus 1, like this. Okay, and so we're going to see this. We're going to see u of x plus h is equal to sums like this. So I want to do explicitly how we're going to apply this and write out the terms somewhat explicitly. So we're going to have u of x plus h. U of x plus h is equal to u of x. So if I just look at the first two terms, the first three terms, I should say, we're going to have u of x plus u prime of x times h plus u double prime of c, where c is somewhere between x and x plus h, times h squared over 2 factorial, which is just 2. Okay, now notice something that we can do here. We can also look at u of x minus h. Now when we look at u of x minus h, how are things going to change? Well, we're still going to have u of x. But that h now is not going to be h, it's going to be minus h. So this is going to be minus u prime of x times h. And then over here, that h as well is going to be minus h. But minus h squared is just h squared, so it's going to be plus u double prime of eta times h squared over 2, where eta is some number between x minus h and x. Okay, now we can also extend these. Okay, so if I wanted to look at this, I could extend this to u double prime of x times h squared over 2 plus u triple prime of c times h cubed over 3 factorial, which is 6. And then down here I could do plus u prime of x times h squared over 2. Now again, for the term down here, I'm going to plug in minus h cubed, which is going to give me a minus sign here, u triple prime of eta times h cubed over 6. And the important thing is that because c and eta, these are not necessarily going to be equal to x. It's something between, in this case, it's something between x minus h and x. and here it's something between x and x plus h. So because these are not x's and they're just some number in between the two, these are exact formulas. This equal sign is not wrong. These are exactly equal to each other. Now, if x is fixed and h can vary, then this is going to change with h. So it's a function of h, all right? But these are exact formulas here. And then if we know some properties about the third derivative of u, if you know the third derivative of u is bounded by 1 or bounded by some constant, then we can understand what the error is between u of x minus h and the approximation obtained using these first three terms right here. It's going to be bounded by the absolute value of the third derivative of u times h cubed. And then we're thinking about h getting smaller and smaller and smaller. So as h gets smaller, h cubed gets smaller even faster. Anyways, now I'm going to switch back to the video that I was making before on approximating derivatives with finite differences, but you got to know a little bit about Taylor's formula for some of those things to make sense. So what we're going to do, everything is pretty much based on approximating the derivative with differences instead of a limit. So let me just remind you that the derivative u prime of x is equal to the limit as h goes to 0 of u of x plus h minus u of x over h. We can also write this as, well, okay, we're just going to look at it like this. This is sort of the fundamental definition of a derivative, u of x plus h minus u of x over h. And so one thing that we could do, just immediately see then, is that if h is small, this is going to be approximately equal to u of x plus h minus u of x divided by h. If h is small, u prime of x is roughly equal to that. And that's basically going to be what derives this approximation. But we're going to do things a little more quantitatively in the sense that I want to be able to understand what the error is. What is the difference between u prime of x and this estimation here? And so what we're going to do is we're going to look at one of the most important tools that we have, which is going to be Taylor's theorem. So Taylor's theorem says the following. I'm going to show this in sort of two different ways. So if we look at u of x plus h, by Taylor's theorem, u of x plus h is equal to u of x plus u prime of x times h plus u double prime of some number c, where c is between x and x plus h, times h squared divided by 2. Okay, and then similarly what we can do is we can look at u of x minus h. And by Taylor's theorem, this is going to be u of x. Now notice what's going to happen over here. That h is minus h. So it's going to be minus u prime of x times h. And then notice what's going to happen here, though. H squared is going to be minus h squared, which is just h. So now it's going to be plus u double prime of, I'll say, eta, where eta is between x minus h and x, h squared divided by 2. Now what I want to do is I'm going to subtract this equation from that equation and solve for u prime. So I'm going to subtract this equation from that equation and solve for u prime of x. So what I'm going to do, what I'm going to get when I do that, I'm going to try to keep things color-coded. That seems to be something that I'm doing today. This minus this is going to be u of x plus h minus u of x minus h. Okay, what's this going to be equal to? U of x minus u of x is 0. U prime of x minus u prime of x, that's going to be 2 u prime of x times h. And then over here, okay, we're going to get Getting a little carried away with the color coding. U double prime, but I feel that I cannot stop. U double prime of C plus U double prime of eta, and then all of this times the common h squared divided by 2. Okay. So now what we're going to do is we're going to solve this for u prime of x. So if we solve this for u prime of x, okay, we're going to divide by 2h and move this over. I'm going to switch it around so that u prime of x is on the left-hand side. And so we're going to have u prime of x. U prime of x is going to be equal to, oh boy, back with the color coding. U of x plus h minus u of x minus h divided by 2h. And notice this right here is basically the difference quotient, but instead of going from x to x plus h, it goes from x minus h to x plus h. This is sort of the center difference quotient, okay? And then we need to subtract off this part here. So it's going to be minus u double prime of c plus u double prime of eta. Okay, now what are we going to get? Well, we need to divide this by h. So it's going to be, we need to divide this by h over 2. So we're going to get times h divided by 4. Okay, and so now what happens as h gets smaller and smaller and smaller, this we know is going, this, as h gets smaller and smaller and smaller, this is going to 0. Okay, so what happens then is that the error between u prime of x and this estimate here is something that is on the order of h, according to this formula here. So this gives the following estimate. This says that u prime of x is equal to u of x plus h minus u of x minus h divided by 2h plus O of h. But we can actually estimate this a little bit better. We can actually estimate this error term a little bit better. So this is an error term, meaning that as h gets smaller and smaller and smaller, the error grows with the size of h. Okay, or sorry, the error shrinks with the size of h. In other words, the error goes to 0 as h goes to 0. The error in this approximation goes to 0 on the order of O of h as h goes to 0. But okay, so here's how we can make this approximation a little bit better. Let me, I'm going to have to squeeze in my work over here. So we can look at more terms in Taylor's theorem. And if you look at more terms in Taylor's theorem, we're going to get u of x plus h is equal to u of x plus u prime of x times h plus u double prime of x times h squared over 2 plus, let me make sure I have everything here correctly, plus u triple prime of c times h cubed over 6. And over here, what we're going to get when we do u of x minus h, we're going to get u of x, and then again it's going to be minus u prime of x times h, but minus h squared is just h squared, so this is going to be plus u double prime of x times h squared divided by 2. And then now for the third term here, the third order term, is going to be minus h cubed, which is going to be minus u triple prime of eta times h cubed over 6. Okay, and now notice what's going to happen. I'm going to erase this. Notice now what's going to happen when we subtract the second equation from the top equation. So when we subtract the second equation from the top, the bottom equation from the top equation, we're going to have u of x plus h minus, sorry, let me do this with black, minus u of x minus h. Okay, now what is this going to be equal to? Well, u of x minus u of x is equal to 0. So then we're going to have u prime of x minus u prime of x. So this is going to be 2 u prime of x times h. Then we're going to have u double prime of x minus u double prime, u double prime h squared minus u double prime h squared. Those are going to cancel. And then we're going to have plus u triple prime of c minus u triple prime of eta, and then all of this multiplied by h cubed divided by 6. Okay, now we're going to do something similar to what we did before. We're going to divide both sides. We want to solve for u prime. So if we divide this by 2h, we're going to have that. This is going to go away, so you're just going to have u prime of x here. And over here, when we divide h squared, when we divide h cubed by h, we just get h squared divided by 12. Okay, so now what this is saying is u prime of x, the error between u prime of x and this estimate, now the error is O of h squared, which is better than O of h as h gets smaller, right? If the error is 0.1 if the error is 0.1 squared, instead of 0.1, the error is going to be much smaller. So here the error between u prime of x and this estimate of its derivative is going to be h squared over 12. So it's a quadratic error. It is an error order of h squared. So u prime of x is equal to u of x plus h minus u of x minus h divided by 2h plus an error that's O of h squared. So practically speaking, what this means is if I want to cut the error, is that if I cut h in half. So if I'm approximating h as being small, let's say h is equal to 0.1, or let's say 0.2. If I cut h in half to go from 0.2 to 0.1, the error decreases by a factor of 4 rather than a factor of 2, using this approximation method here. So once again, if I'm approximating the derivative with a difference like this, if I cut h in half, okay, so I get a smaller value of h. If I cut h in half, the error does not cut in half. The error gets divided by 4, okay, according to this formula right here. So we say this is a second order approximation. Okay, so this is great for the first derivative, and it's going to come back. But what about the second derivative? How can I do this with the second derivative? There's going to be two different ways I want to look at it here. The first is I want to look at this. I want to use this approximation here. So I first want to use this, the approximation to the first derivative. So u double prime of x, well, is equal to the derivative of u prime of x. So this is equal to u prime of x prime. Okay, so what I'm going to do is I'm going to apply that finite difference that I just saw to u prime. So this is approximately going to be equal to u prime of x plus, and instead of doing plus h, I'm going to do plus h over 2. So plus h over 2 minus u prime of x minus h over 2 divided by, what's going to be 2 times h over 2, so divided by h. Okay, and I know the error here is going to be O of h squared. Okay, and now what I'm going to do is I'm going to approximate each one of these. I'm going to use a finite difference approximation to approximate each one of these. Okay, so I could say, if I want to be more precise, so this is approximately equal, I could say it's equal to this plus O of h squared, something like that. But instead, I'm just going to write this approximate equals. Okay, but now what I'm going to do is I'm going to apply the finite difference approximation, the u of x plus h minus u of x minus h, to each one of these terms right here. So in the numerator here, when I use a finite difference to approximate that, I'm going to use h over 2 again as my adding value, not h, but h over 2. And so when I approximate this, I'm going to get u of x plus, I'm going to add h over 2 to this, so it's going to be x plus h, minus, I'm going to subtract h from this, or h over 2 from that, so it's going to be u of x, so minus u of x. Okay, and then for what's going to happen over here, for u prime of x minus h over 2, well, I'm going to add h over 2 to this to give u of x, so it's going to be minus u of x. And then, again, when I'm doing this approximation here, I'm going to subtract h over 2, which gets me down to u of x minus h. But there's a minus sign there, so it's going to be plus u of x minus h. And this, for this approximation, that's divided by h. And for this approximation, that's divided by h. And all of this is divided by h. Okay, so look at this, write it down, and we can simplify it in the following way. We can simplify this as u of x plus h minus 2u of x plus u of x minus h divided by h squared. Okay, so this is going to be the sort of fundamental thing that we use to approximate the second derivative. There are other ways to approximate the second derivative, but the advantage of this is that this has, again, a quadratic error. The error between u double prime of x and this is equal to, is O of h squared. Now, one way that we can see that it's O of h squared is to do this Taylor thing again. So let's look at another way that we can derive this approximation. If you look at the Taylor formula here, I'm going to take it now to the fourth term. So I'm going to have plus u triple prime of x times h cubed over 6, and now plus u 1, 2, 3, 4 of some number c between x and x plus h to the power of 4 over 24. And then what's going to change down here? Well, it's going to be minus, because it's, it's going to be minus h cubed, which is h cubed times minus 1. And we're going to get u triple prime of x times h cubed divided by 6. And then plus u, the fourth derivative, eta times h to the power of 4 over 24. Okay, now we're going to do something similar to what we did before, except instead of subtracting the equations, we're going to add the equations together. So we're going to add these two equations together. So we're going to have u of x plus h plus u of x minus h on the left-hand side. Okay, what's going to happen on the right-hand side? Well, u of x plus u of x is going to give give 2 u of x. Okay, u prime of x times minus u prime of x, those cancel out to be equal to 0. Then we're going to have the sum of these two together. So we're going to have plus, we're adding these two together. These are the same term, right? There's an over 2, but we're adding them. So it's 2 times over 2. And so this gives us u double prime of x times h squared. Okay, and now to be brief, what I'm going to do is, when we add these two together, again, we're going to get cancellation. They're negatives of each other. And so then what we're finally going to get is just the sum of these two terms, which is O of h to the power of 4. Okay, because there's going to be some constant times h to the power of 4. Okay, that's what that means. Okay, so now again, we want to solve, or not again, but similarly to what we did before, we want to solve for u double prime. So let's see if we divide both sides by h squared. This gets divided by h squared. This gets divided by h squared. That goes away, and now this is just O of h squared. Okay, and if we subtract that from the other side, that gives the exact approximation that we had before. And so it says that u double prime is approximately equal to this minus that with a quadratic error again. Okay, so what we are going to do, and we'll look at this in the next video, this gives us an approximation to the derivatives. We are going to approximate the derivatives here we're going to approximate actual derivatives with these differences right here. We're going to do this on an interval, and we're going to show what to do after that point. But bottom line here is that we're going to approximate the derivative, both the first and second derivative. Second derivative is the only thing that we have here. We're going to approximate that with these finite differences.